Janhunen. Okay, it's about asteroid touring nanosat fleet with single-tether E-sails. Okay.
Okay, good morning. So, indeed, my presentation is about a particular mission architecture which is intended to produce data from a potentially large number of asteroids. And this feat is based on so-called Coulomb drag propulsion idea, which means that one uses some natural space plasma flow for propulsive purposes with the help of a charged thin tether which taps momentum from such flow by deflecting the ions of the plasma. And there are basically two application domains for such Coulomb drag propulsion. If one applies it in the solar wind, in the interplanetary regime, then one gets the so-called electric sail or E-sail. If one applies it in low Earth orbit, then one gets so-called plasma brake, which can be used for satellite deorbiting at low cost. And the reason why this is interesting is that this is, roughly speaking, order of magnitude more efficient than existing propulsion methods. If one measures efficiency in terms of the total lifetime integrated impulse produced by the propulsion system divided by the propulsion system's own mass. Here are some images of a particle in cell plasma simulation of the E-sail in solar wind. So at the middle there is a tether, so the tether is perpendicular to the simulation plane here, and then the solar wind ions and electrons react to the presence of this charged tether. I mean, actually not to the tether itself, but the electric field of the tether, in such a way that we get some kind of bow shock in the plasma and then a wake. So this is, qualitatively speaking, similar to aerodynamic interaction between a cable and flowing air. But the crucial difference here is that the effective size of the obstacle, this tether, can be much wider than the physical width of the tether. So the tether can be made of a few tens of micrometer metal wires, but the effective width can be about 100 meters in the solar wind. So the effective obstacle size is about 100 meters, and that makes the effective sail area very large. And this is this is the reason why this method can be efficient. There are also some relevant laboratory experiments which have been performed, and actually not to address this particular problem, but as a byproduct of these published results, we can infer certain things about this Coulomb drag propulsion which are in good agreement with the plasma simulations of the previous slide. There is Cubesat testing in low Earth orbit going on of this technology and this physical principle. So the Aalto-1 Cubesat was launched in June this year, and it contains 3 experiments. One of them was described in earlier session here today. That's the hyperspectral imager. But we also have our Coulomb drag experiment on board. It consumes about 300 grams of the satellite's mass, and it's distributed in 2 PCB cards, so-called high voltage board, and then the so-called motor board, which contains the reel, tether reel, which is motorized reel, and its intention is to deploy 100-meter long tether, and we expect this experiment to commence later this year, depending on the developments that are ongoing with the satellite bus and its software. And then as a forthcoming mission, we have EastCube-2, which is supposed to, where our task is to deploy a 300-meter long tether. Okay, so now I go into the core business of this mission idea. So we would have a single-tether E-sail in the solar wind. So we have a nanosatellite and then pretty long tether up to 20 kilometer long, and then some remote unit end mass, and then we rotate the system slowly, about 1 hour rotation period, and then we can produce some millinewton level of thrust at one astronomical unit distance from the Sun. And then I won't go into details, but by using a certain geometric arrangement regarding how the tether is attached to the spacecraft and so forth, it's possible to point the spacecraft without moving parts. So we can have a fixed telescope at one end of the spacecraft, and we can orient this telescope towards the target regardless of the rotation of the tether. So we can rotate the spacecraft over 2 axes just by using momentum wheels. And this is possible if the tether is attached to the center of mass of the spacecraft. And then we could fly a large number of these satellites in order to look at a large number of asteroids, in order to take seriously the fact that there is a very large number of asteroids, many of which would be relevant targets for study, not only for science but also for asteroid mining. And here we would launch them first of all to marginal escape trajectory, and then each spacecraft makes a quasi-elliptic tour through the main belt, lasting about a bit more than 3 years. During this tour it can fly by on average 6 or 7 asteroids. And then at the end of the tour the spacecraft returns to Earth's vicinity again. So we make an Earth flyby at the end, and this is to retrieve the data. So we store all the data in memory and then we retrieve it at once during one flyby. And this is a key point of this mission because it makes it affordable. So we need only about 3 hours of Deep Space Network time per spacecraft in order to return the data. And this idea was presented with the name Multi-Asteroid Touring to European Space Agency's so-called call for new science ideas last year, and it was selected for further consideration this year. So this selection means that a workshop was arranged at ESA 2 weeks ago, internal workshop where this idea was discussed, and then likely it will lead to some kind of CDF study later this year. But this discussion is still going on, that ESA also wants to expand the concept a little bit, so they are also looking at other related concepts at the same time, not only this particular mission concept. Then some words about mission design of such mission. So for example, how could one in practice select the targets and so forth? So we could, for example, have 25 primary targets, so it means that each of the 50 spacecraft has 1 primary target. And then we could devote 2 spacecraft per target. That's to have some redundancy and to increase the fraction of surface of the asteroid that can be mapped during those flybys. And also, in case the asteroid has a moon, then if we have 2 flybys, then we can determine the mass of the asteroid by observing the relative position of the moon with respect to asteroid with significant time difference. And of course, it's to be expected that we will discover these new moons. So not all asteroids are known to have moons when we start, but we probably find small moons, and then we can, in some cases, be able to determine the mass of the asteroid. And then, okay, so 1 primary target per spacecraft, but then 5 or 6 other flyby opportunities, so about 300 altogether, and these form essentially a random sample of the numbered asteroids. Random because we are not able to select them freely. The primary targets can be selected freely, so they can be globally the most interesting bodies in the solar system, in the main belt. And then we also, during cruise phase, when we do this optical navigation, as a byproduct, we also discover many small asteroids, and this data will produce the number density of small bodies in the main belt. And this is a currently unknown parameter, and it's an important parameter because this population is the source population of near-Earth objects. And then last but not least, we can also do cruise phase science. So from the E-sail housekeeping data, we can infer the solar wind density and also velocity within some approximation. And this, if we have 50 measurement points distributed in the heliosphere, this gives a pretty interesting data set for the instantaneous structure of the heliosphere. So here are my conclusions. So it's a low-cost mission concept to make a flyby study of a potentially massive number of asteroids. It's low cost because the only cost per spacecraft is the incremental manufacturing cost, I mean the recurrent manufacturing cost, and the launch cost to marginal escape orbit of about 10 kilograms per spacecraft, including this this P-pod launch system. And then the operations costs are manageable. I mean, I would say low because we make this Earth flyby, and this is really a crucial point of this mission architecture. I think that without returning to Earth's vicinity, it's not feasible to operate so many spacecraft in deep space, just because of costs. And this is enabled by the E-sail, single-tether E-sail in particular in this case. The E-sail technical readiness level is still relatively low, so we need a Pathfinder Cubesat E-sail mission in the solar wind in order to make this happen. This also depends on automatic navigation, but such navigation was actually demonstrated already by Deep Space One, so it's not really new technology in that sense. Okay, thank you very much for your attention.
Any questions for the speaker? Yes.
Tried your E-sail with SQ1.
Yeah.
What did
What happened, you mean?
what happened?
Something went wrong.
What was wrong?
Yes, what went wrong was that there was a mechanical problem with the slip ring of the reel. So the reel did not rotate. And we later discovered the reason for this in vibration testing. The reason for this was that SQ1 was a very low budget mission, student satellite mission, so we did not have opportunity to do proper testing before flying it. So it was the fly first and then fly against Cubesat strategy, risk strategy. So it was a rather trivial problem, which was not really, it was in our part of the hardware, but it was not really related to the E-sail as such.
Okay. Any other question? I have a question for you. So you're envisaging launching hundreds of these. 50. So it'd be one launch with all these on one spacecraft, or it'd be multiple launch?
It can be either one. So in this example, we considered one launch just because the smallest launch vehicles which are capable of going to the marginal escape orbit can launch about 500 kilograms to that escape orbit, or a little bit less perhaps. But obviously we could also use piggyback opportunities. So this is fully scalable mission. So if one doesn't want to launch all of them at once, you can launch any of them at any time, piggybacking on any launch vehicle which goes outside Earth's magnetosphere, because the E-sail starts to work only outside Earth's magnetosphere, because inside magnetosphere there is no solar wind. So that is the only requirement we have.
Very interesting. All right, thank you. Let's thank the speaker again.